আজকে আমাদের ক্লাসের ম্যাটেরিয়াল গুলো নিয়ে একটু যদি ডিসকাস করি। লাস্ট দিন আমরা পড়েছিলাম reciprocating pump নিয়ে, and that kind of concludes all the syllabuses we need to cover. And now we are going to talk a little bit about the cycles and how the cycles are designed. So let me get my pen. So first of all, there is a Carnot cycle. Carnot cycle. So Carnot cycle is basically dependent upon the fact that it is reversible process. It consists of mainly 4 processes, and all of them are reversible processes. 2 adiabatic processes. Carnot cycle consists of mainly 2 adiabatic processes and 2 isothermal processes. Okay, so of these 4 processes, all of the processes are irreversible, reversible. Okay, that means if we want to go from one state to another, we can easily go from one state to another and vice versa. Okay, so irreversibility means we cannot irreversibility means the process cannot be run in opposite direction. Okay, so that is all about the Carnot cycle, and we are now going to see the indicator diagram, which is commonly known as the PV diagram. So this is my P. P stands for the pressure, and V, the x-axis, stands for the volume. So there are 2 isothermal lines. Okay, this one is in temperature TH. So this temperature is high and hot, and this is lower temperature. Okay, so the adiabatic process is not isothermal. That means the temperature will either rise or it will decrease. So from this point to that point, there is an adiabatic expansion, and thus the temperature lowers to TL. Okay, then after careful compression in isothermal process, it goes here, and after that, to complete the cycle, we need to again compress it and reach the initial temperature point, which is 1, 2, 3, 4. Okay, so this is it. 1 to 2 is an isothermal process. Meaning the temperature will remain same on that line from 1 to 2, and it will TH, right? So the temperature is TH. Okay, at from 2 to 3, It is an reversible and adiabatic. I think all the processes are reversible, so we don't need to take account that in separately. So 2 and 3 process is an adiabatic process. Adiabatic expansion process. From 3 to 4 is an isothermal heat rejection process. Okay, and this one is isothermal heat addition process. So we want to take a heat from a top and the source temperature TH, and we will need to reject some of the heat at our lower temperature. So that's how the cycle is going to operate. Okay, finally the process is 4 to 1, which is adiabatic compression. So 4 to 1 we get adiabatic compression. Okay. So we need to get into account the entropy and temperature diagram. To do that, we need to account what the entropies are same and the temperatures are same. We can see the 1 to 2 is the isothermal process, and if the heat is adding up in this process, the heat is Q input. So the heat is Q input and Q out is at from 3 to 4. Okay, so 1 to 2 the entropy will rise, but the temperature will remain the same. So if you want to draw the process on the TS diagram, T and S. Okay, so from 1 to 2, the temperature will remain same, but the entropy will rise. Okay, so that's it. From 2 to 3, there is the adiabatic expansion, and the entropy will remain same. The temperature will drop to TL from at 3. So we get a vertical line, which means the entropy is same from 2 to 3, and the temperature drops to TL. Okay, from 3 to 4, the temperature is again TL, and the lower temperature or the sink temperature. So again, the temperature will be horizontal to the x-axis. That means, okay, so 3 to 4, the temperature will remain TL, and from 1 to 2, the temperature will remain TH. Okay, so far so good. And to connecting the dots, there is a adiabatic compression. That means the entropy of 4 and 1 will be the same, and due to this adiabatic compression, we get an adiabatic compression process. So the temperature will rise again to the higher temperature. So from 4 to 1, there is a vertical line telling us that the entropy at 4 and 1 are the same. So this is the Carnot process in TS diagram. Okay. Moving on to our next cycle, which is Stirling cycle. Okay, all the cycle we are talking about, all the cycles we have been doing in this module or in this lecture, it's all about I can say, what we can say is that all these cycles are designed for uh, for modeling of the situation in the real life. Okay, so all these cycles are not practical, rather than it is used to model the cycles in easier form, so that we can calculate the efficiency and all that. So in the Stirling cycle, the heat addition process will be the same. There always will be two isothermal lines. So in PV diagram, there will be two isothermal lines. Okay, two isothermal lines, and the heat addition process will be in isobaric process. Okay, so isobaric process, that means the volume will be the same at these 2 points and these 2 points. That means from 1 to 2 there will be isothermal expansion. From 2 to 3 there will be an isobaric compression. It won't be a compression process, rather it will be a isobaric process from 2 to 3, and from 3 to 4, there will be again an isothermal heat rejection process. So the heat addition will be from here at Q in, and Q out will be from here. Okay, so same as before, that this is the temperature TH and TL, the two temperature line. Okay, the two isothermal line. So the cycle is operating between these two temperatures. Okay, then again, if we want to draw the TS diagram, okay, the TS diagram will look like something like this. So this is my temperature side, and this is my entropy side. Okay, from 1 to 2, the temperature will remain same, but the entropy will rise. Okay, then 2 to 3, there is the isobaric process. The entropy will as the temperature is decreasing, the entropy will reduce, and we will get 3 point like this. From 3 to 4, there is the isothermal heat rejection, and again, to connecting the dots, we need to just 4 to 1. So 1 to 2 isothermal heat addition process, 3 to 4 isothermal heat rejection process, and 2 to 3 and 4 to 1 is isobaric process. Okay, this arrow I have missed. Okay, so this concludes the Stirling cycle and the Carnot cycle. Okay, the thing is, here the volume is constant. Okay. So far so good. So there is a heat addition process here and here. Q out. Okay. So far so good. Okay, then there's another cycle, which is Ericsson cycle, which is actually kind of same, but instead of this iso there will be two isobaric processes rather than same volume processes. So there will always be heat addition in the two temperature sources, the TH and TL. So we need to consider those in the PV diagram also. So in Ericsson cycle, this is P, this is P. So there will be pressure two pressure line, okay, and two isothermal lines. So isothermal lines like this, okay. Actually don't need this. So heat addition process will be here, because this is the isothermal line, it is again TH and this is TL. So Q in energy is the input and this is Q out. Okay, then from 1 to 2 there is isothermal process, 2 to 3 isobaric process, but the pressure will be same from 2 to 3, and then 3 to 4 again isothermal heat rejection, 4 to 1 and 1 to 2. Okay, so if we again want to draw this in the TS plane, okay, from 1 to 2, from 1 to 2, 0.1 and 2, right? So from 1 to 2 the temperature will be same, right? Okay, from 1 to 2 the temperature will be same. From 2 to 3, the pressure will be same, okay. So the pressure will be same, and again if 2 to 3 it's lowering the temperature, the entropy will decrease. So it will kind of look like uh, previous one, but instead of V constant, pressure is constant, okay. Pressure is constant at these 2 points, 1 to 4 and 2 to 3. Heat addition process will be here, Q input here and Q output there, okay. So that sums all the processes, all the ideal processes we should have been discussing before, and this kind of concludes all the cyclic processes in thermodynamic analysis and heat transfer. And I think for all that process, for all these cycles, the efficiency. Okay, there's another thing. I forgot to mention it. I forgot to completely mention it. That is that there is a regeneration. Like when 2 to 3, there is a heat rejection process, right? It lowers the temperature from TH to TL. So there is a regeneration heat which is actually heating this 4 to 1 process. Okay, so there is no outside involvement of pump or compressor, because this is an ideal cycle. That is why we are modeling it as a regeneration. So this cycle is actually running on these two temperature limits, the TH and TL, and thus it's producing some useful work, which is Q in minus Q out, obviously. And there's no other addition of heat addition from 4 to 1 or 2 to 3, because 2 to 3 heat rejection is actually accumulating and it is giving to 4 to 1 process, so it regenerates to 4 to 1. And same process is going for that process, where in iso volume process the regeneration is like this. From 4 to 1 the temperature is rejecting some heat, and this heat is actually heating up to 4 to 1 process. So this is regeneration in this process, and in TS diagram it is this. So this heat is regenerated, okay. So due to regeneration, we don't need to talk about 2 to 1, 2 to 3 and 4 to 1 process. Okay, this is internally is reversible, and we need to only think about the TH and TL, because we know the highest Carnot efficiency is 1 minus TL over TH, right? or or actually the cycle is 1 minus Q out by Q in, right? But due to heat addition in these processes, we know the entropy is same, and this why it is actually efficiency of this. It only depends on the upper and lower limit of the temperature in the cycle. So I think that's good enough. We have actually kind of concluded the lectures in fundamentals of mechanical engineering within very short period of time, and we have very good time together. I think we will use all those topics in our exam, and I think my hopes are that you will always be able to use this in your real life too. Okay, goodbye.